Okay, hi, and welcome to CS6000. I am your instructor, Terry Bolt. Many of you know me, some of you don't. I'm going to start by telling you a little bit about my background, and then we have more students than I would normally go around the class and do an introduction, but I feel it's worth the time for you to get to know a little bit about the other people in the room. So we're going to start with me, and then I'm going to combine, rather than going around the room, I'll go with who I have in the roster, so I'll also use this as a way of, now we'll just go around the room. I can match them up. So some of you have already met me. I am been a professor for a long time. I got my PhD from Columbia University in 1986. I stayed on Columbia's faculty for 8 years. I moved to Lehigh, where I founded their computer science department, and I was a faculty member there for 9 years, and I moved here in 2003. So I've been doing this academic thing for quite a while. I've also done, I worked for big companies like AT&T and Siemens, on the side while I was a faculty member, and then I've done 3 startup companies, so I've also understand some of the practical applications of this. I actually designed this class, and this is our 4th offering of it, to improve both the efficiency of the PhD program and to give students who are thinking about PhDs an opportunity to get involved in some of it and sort of see where it's going to go. And that's because the core of computer science research methods are shared across all the subfields. In fact, we have some people here who are not computer scientists. Some of what we'll talk about in this class could be applied in EE. You could actually apply it in psychology, for that matter, for some of it, although they have a few things that are different. So understanding how to do research has a bunch of skills that are not very tied to your particular area. So as we go through this course, we're actually going to have some high-level objectives. So the first, and we're going to start today, is actually some publishing and development tools. This might seem really boring and beneath you, and I'm sorry if it feels that way, but I want to make sure everyone starts off on the same ground of you know how to do LaTeX, you know how to do Git, because we're going to use it for all your homework assignments. So if it's a little bit slow today, don't worry, we'll make it up later. And then we'll talk about how to effectively, so next week we'll start on how to read research papers, then we'll have a couple of weeks where we'll talk about how to write them, and then we'll actually talk about how to develop a thesis proposal, something you'll have to go through, so what goes into an effective proposal, how to design and experiment the statistical analysis and the result, and doing statistical analysis of the resulting stuff. This starts to get more technical. There will be some added reading in here because I want everyone in this class to understand how to actually drive an experiment that shows what you want it to show, not just have some numbers that look pretty in a graph. That might get you published, but in the long term, that's not going to get your work to be cited and built on, so you're going to want to do that. This year I'm adding, compared to the last time I taught this, we're going to have a homework assignment and some lectures on how to actually use cloud computing, because you will probably reach a point in your career when you're going to have to use it, or it's going to be cost effective to use it. You might not actually have 30 processors at your beck and call whenever you need it, but you can fire up Amazon Web Services or Google Cloud and have 30 processors in 15 minutes if you know how to do it. So I'm going to make sure you all know how to do that. This way you're not stuck with, oh, I can't afford to compute that. That's a pretty lame reason to not do an experiment in your thesis. So we want to make sure you know how to do that. In this class, you'll be getting some added Google Cloud credits and Amazon Web credits. So you'll have like the normal free account for Amazon's $100 worth of credits. With the class, you'll get another 100, I think, or another 50. So you'll have enough room to do some moderately good experimentation. But I'll go through how to set it all up and how to make sure you know how to do all of that. And we also want you to get an appreciation for an understanding of the different subfields of computer science and their approach to research. So we'll have a number of guest lectures, either from students or faculty in different sub-areas of computer science. If there's a particular faculty member whose research excites you, write to them and say, are you going to talk in CS6000? Because you'll want to hear it. Because so far I only have 2 volunteers. But you know. It doesn't matter. I can get people from outside. I can get graduate students to go and give talks. And you know, with all of you in this class, if each of you gives a talk, we'll have a lot of time doing that. So it's not critical that I have everyone. So if there's somebody particular, and if you don't want to contact them because that feels a little uncomfortable, ask me. Okay. So my research area, my primary research is in computer vision and machine learning. I have actually a very varied career in computer science research. So I've done theoretical computer science, I've done networking and systems, I've done security, I still do some security, I've done lots of vision, lots of machine learning, and I've also done and published papers in psychology. and I even have a couple of published poems. So I'm all over the place. Not necessarily the most efficient way to move up, but I'm also a well-published author and an IEEE fellow. So when I talk about how to do some of these things, I actually have the experience. I may not look like a normal professor to you. At least I'm not wearing colored Crocs today, but you know, actually, CS faculty come in lots of shapes and colors, and there's lots of them that are eclectically dressed. So now we'll go around, and because you guys started at the back of the room, we're going to start with you. So let's see if I can. Okay, Alan? Howie. Okay, so Howie, tell us a little bit about yourself. What are you here for? Oh, no, don't leave yet. No! You have that effect on people, Howie. So. This is going to be an odd room to be in if we keep doing that, but.
Tom Hastings, I graduated in May with my master's in software engineering. I worked for, well, I started with Miner, and Monday doing more of the, it's called CAPS, and more of that's creating vulnerability type of stuff. What I know is my second year, my PhD, and I use like containers and pipelines. This is my student, it's my second year PhD. My research area focuses on blockchain. I'm also I just started as a professor over at College Business, first semester of teaching.
So don't use me as a guide.
I'm wearing a tie. Look at me. That's different.
In College of Business, you got to dress like that, right? So.
Well, my name is Mark Ashley. This is my first class PhD in security. I work as a security solutions architect. My name is David. My second year will be using as well. Research using data encryption. I'm Adam, PhD student. My research is in software security, software exploitation. My background is in malware and
So I'm going to actually take a quick break because I forgot to mention something before we did this because no one's taking notes. That's not terribly a bad thing. But in a couple of weeks, when you start writing your paper, you're going to have to find a partner in this class to do shared reviews. Right, so you might want to know who's doing work close to yours because it's much more interesting for you to review if you're in security, a paper in security than one in, say, vision. So, I can't hear a word you're saying over here. But okay, what area of computer science you're interested in? Okay. And so again, say what area you're interested in. So second year doesn't tell me what fields you're interested in. Deep learning? Can you speak up?
David, I'm second semester PhD student. I'm doing software engineering, software testing.
is cloud computing.
Yes. My name is Hannah. It's actually Martina, but I go under Hannah because I absolutely nobody say that correctly. I am a PhD student, but I hope to pick up a master's on the way. My interest is in artificial intelligence and machine learning.
I'm Claudia Loco. I am just finishing up my master's this semester and starting
So I'm second year PhD on doing research on batteries.
I'm Steve. I do research in computer vision / machine learning, and I am teaching a course in the undergraduate program.
My name is Ahmed. This is my third year. I'm interested in the Mac vehicles and battery methods.
Abdullah. I just started my third year in my PhD in engineering security, and my interest goes into the name, data, and encryption. Not a lot of students know about it.
Hello everyone, my name is Daniel. Second year PhD student. I finished my bachelor's in computer science and information systems, and finished my master's in IT. Then I realized I want to do ML and AI, so these days I'm probably focusing on deep learning and attention mechanisms, vision, and neural machine simulation.
My name is Mom Singh. I'm a PhD student, second year. My concentration is computer architecture because I kind of hate computer boot up too slow because my definition is if a computer boot up can take longer than a man would drown with water, that computer is useless.
I'm Ryan Harris. I'm a master's student that is thinking about getting my PhD sometime soon. My interests are in efficiency and optionality, and I teach computer science and Central and computer science.
Katrina. I'm a second year PhD.
Okay, so that gets you an introduction, gives me a feel for a little bit who's here, and I'm trying to match names with old photos, so sometimes it's the photos I have of you is not quite where you are, so I got to learn how to make those decisions. So a couple things, I will butcher even just Hannah, that's tough for me. Later I'll call you some other name that probably begins with an H. Okay, I am dyslexic, so when we talk about writing and issues, right, I'm dyslexic. If I get the first letter of a word, it means I know what the word is. Everything else after that is random perturbations in my head. Sometimes I'll get the last letter and a few in the middle. Like if there's a couple of ups and downs, but words and letters don't mean a whole lot to me, so it's very challenging. So, don't take it personally if I butcher your name or if I just get close. Okay. So all of this probably will be recorded in today's lecture, so you can dance at home. And so all the classes will be recorded. We have a couple of students who, for work or whatever, are traveling. Don't worry if you have to miss a class unless you're scheduled to give a talk that class. It's not going to be a big deal. You can watch them later and catch up. The sort of ground rules for this class are: there's work. Your PhD students, I'm not going to chase after you. This is not a freshman or sophomore level class. Your work should get done when it gets done. If you have questions, ask me. I have office hours, which I will get to sometime in a little bit. I thought there was the next slide, but so your primary goal here is to make sure you understand stuff. So don't go by for too long. If I'm talking about something and you don't really understand it, stop and ask, or at least make a note of it and ask me later. Don't be embarrassed. Don't be afraid to ask. You asking questions now are the whole reason for this class, so that next semester or even this semester when you're working with your advisor, each of you don't ask the same question to each of your advisors, which multiplies the loss among all the faculty by a factor of 10. So if there's something you don't understand, ask it now. We'll go through that. It's okay to ask by email. If you ask anonymous questions by email, which I had last time I taught this class because people felt the question was too dumb, they didn't want to put their name on it, so they sent me mail from a random Hotmail type of account. That's okay, I will still answer it in class, so you can maintain your anonymity. If that's the only way you want to ask your question because you think it's that dumb, I'll bet you're not even the only one in class. But so please go ahead and ask. When you're interacting with respect to other students in this class, be constructive. You can try and be constructive with me. It falls off. It's really hard for me to know. If you have things to make this class better, go ahead, give me constructive criticism. We'll have lots of time when you as students will be talking, and then really do try and be constructive. So you don't even always have to ask a question. You might be making a comment, which is constructive criticism, and that's good in this class. But you can do it in a way that's polite. And don't be afraid, but don't be too polite. Some of you might have a upbringing that makes you want to not criticize other people or not say anything bad. If people continue going down a bad path, you're not helping them. Your job is to help them. Although I might do it in this class, there will be times when I'll be encouraging you to do it, because you have to learn to become your own self-critiquer, right? And be able to critique other people in your group. So it's a really important skill to find that balance between being overly harsh and being harsh enough so that the point gets through and people recognize this is what you need to fix. Well, we'll go through some reviewing of papers later this semester. And when you're doing that, it's actually really important to be critical. We'll actually have 1 or 2 assignments where you get to choose people so you know what the relationship is and it's in a field you want. And then there'll be 1 assignment when I randomly assign people and it's anonymous. So you'll be getting random criticism from somebody whose name you don't know, because for many people it's easier to be a little bit more honest and critical when their name's not associated with it. Okay, you really want to get over that, but it's okay if you want to do that. Double blind. No, this will only be single blind, but we'll talk about the importance of double blind when we get to actually conferences and whatever. But in this class, it's probably too hard to make it double blind, because if you say, well, I'm working on architecture, right? We've already identified you. So unless you want to write a paper on something completely different, it would be very hard. Okay, so grading for this class. Your writing assignments and papers are your biggest thing. You will have, the writing assignments are little steps towards the final paper. My objective for each of you is you have a paper at the end of this class that is good enough for you to go submit someplace. Okay, now you might be thinking my research isn't there. I'll tell you, your research doesn't have to be there yet. It will be by the time you get there. And that paper might be, and last time I taught this class, more than half the papers were a survey paper. That is, they had no new original research. That's nothing wrong with that. When you do your thesis proposal, when you do your thesis, you have to do a literature search anyhow. So the difference between doing a literature search and writing a survey paper is one involves writing. It's not that big a deal. And as we'll see when we get to citations and whatever, survey papers can actually have more citations and impact early in your career than your own original research. So it's actually a good thing to start building your reputation to do a really good survey. And so maybe that will be what you do in the semester. I'm currently planning on 2 oral presentations, but given the class grew from 12 to 30, there might only be 1, in which case I might adjust the amount down. But if there's not many faculty, we'll get 2 in. And then it'll be 15% of your grade. Class participation and or online discussions. So because not everyone's going to be in class, I can't go with just this. I'll have some discussion boards where I will post questions and they will be a general discussion. That's going to be in addition to your weekly journal, which is 20% of your grade. And each week, each of you will write a relatively short 1 to 2 page journal, not journal paper, but like journal diary kinds of things, like what you learn. You'll see your first assignment is one of those in just a little bit. And then our experimental design assignments and our cloud assignment will be 10%. If I get rid of some of the oral presentations and we go to only 1, then I will move some of those points into your cloud assignment probably so that it has a little bit more weight. For those of you who are not CS majors, which I think was 1 or 2, I will make alternatives for the cloud assignment if you feel you don't want to go down that path. But I can tell you, if you're doing computational anything, having access and understanding how to use the cloud is actually worthwhile to do. But that'll be up to you. Okay. So in this class, you will have many research papers to read and hear many talks. In this class, if the paper you're talking about is published, obviously it's fine to discuss anywhere, even online. We will have times when students are presenting work that is unpublished. I will ask explicitly and maybe even remind you when we have some of those, even if it's been submitted and currently under review, treat that work as confidential. Don't go posting someplace else or talking about it at work that, oh wow, they're doing this really cool GPS jamming system or whatever, right? Might be cool and interesting and the people at work might love it, but this is confidential information within this class, so don't share it until the authors tell you to go ahead. And be ready to put yourself in the mind of reviewer, author, and researcher. We will talk about the mindsets of each of those throughout the semester, and you want to be able to flaccidly move between one and the other and the other. So when you're presenting, you're in the mode of author, but then you're going to put yourself in the mode of the reviewer when you're going the other way around. So, so I'm going to start by setting up your first week's assignment, because maybe it will motivate you to make for the rest of the paying attention. So I apologize for the small font, but I did not notice. That's a wonderfully rendered screen, isn't it? I'll have to remember the first line of every page disappears. So your first assignment. In your week one journal, I will show you some Canvas stuff where that is. How many people here have not used Canvas before? Okay, so then I will show you a little bit more of Canvas, since about a number of you have missed it. I've never used it. But so your first week's journal is going to be done in LaTeX. It is going to be typeset and look like it's part of a paper. And you're going to upload the PDF, in which you will include a link to your Git repo. So those of you who are currently actually registered for the class and show up in Canvas. So if it shows up in your Canvas, an hour ago I sent, or an hour and a half to 45 minutes ago, because it varied over time, I sent an email invitation through Git to each of you, asking you to join my organization called Bolt's Classes, something like that. That will give you access to a Git repo that allows you to have private content without paying. So if you have a Git account already, you don't have to use your UCCS one, which is what I sent mail to. Otherwise, you can use that, and I will show you a link in a minute. When you use the link to the GitHub Education Pack and then sign up with your UCCS email and accept the invitation to join my group, you will get, I think, unlimited private repos, or maybe it's 100. I can't remember what the agreement is. But you'll be able to have private repos, which means no one else can see it except for me, because you're in my organization, which makes our grading a lot easier. I can go in and see anyone's repo. So all of your assignments will be done using Git and LaTeX. And if you have no idea what either of those are, you will by the end of today's class. So you can follow along and see it has some value. You should have your title and author. So as a LaTeX document, you'll have title and author. Your first section contains your goals for this class, your personal goals. What do you hope to learn out of this? It's okay if you say this course is required. That's part of why you're here, but hopefully you can actually come up with something you actually want to get out of this class. What you're studying and something personal about you. I am horrible with names, but I can remember interestingly odd details of students 20 years later. I have no idea what their name is, but I can tell you where they sat in class and what one of their hobbies was, if it was interesting enough that somehow it clicked with me. I have an eclectic memory. And include a photo of yourself. This is your way of practicing including a figure in LaTeX, because you'll have to take a photo, figure out how to get LaTeX to include it as part of your paper. And this week, we're not at all worrying about content. This is all about the tools, so you're comfortable with those. The second session should be about where to find your source code and a little bit about your learning. So you're going to just have a link to your Git repo, either public if you really want it to be, or shared with me through the mechanism I just mentioned. If you put it in my class, it's automatically shared with me, because it's why I set it up that way. And then describe with whom you shared. I don't know what that's. So, and then you should discuss your learning from this week, any problems or struggles you had and how you overcame them. Okay, there will be lots of times when I'm going to give you a generic assignment where you may struggle with it. This week, I'm going to set things up pretty straightforwardly. Hopefully you won't have, but you will get some weird LaTeX error. I guarantee at least one of you will have an error that you cannot figure out, and then you'll go Googling for it, you'll find the answer and move forward, right? That's the kind of thing we're talking about in terms of struggles. There's no deep research in this, just basic syntax. And then finally, you should have a section that contains at least 5 papers that are related to your research area with proper, with 1 to 3 sentence descriptions of it. So a short summary of those 5 papers and a proper citation to it. And you should reproduce at least 1 equation from at least 1 paper and discuss it. This is practicing typesetting an equation, right? And so you know how to do that. And then you should have the paper should end with a properly formatted bibliography reference section in IEEE format. You can use, for this week's assignment, you can use whatever you feel are 5 appropriate papers. This is more an exercise in, can you, very, very short summary, because we'll talk more about reading papers and stuff next week. but can you get LaTeX and do the citations and the BibTeX and whatever? This is really, as I said, this is like Hello World for PhD students, right? It's with a little bit more complicated tools. Any questions about this assignment? Okay. So if you run into problems, you are free to email me with questions. So now let me go out of the grade book. That's not where I want to be. And I'm going to go over here and hit a couple of syllabus things. Okay, so this is my, should have been an email address. Well, my email address will be up here soon. It's tbolt@vast.uccs.edu. I also have a .uccs email edu, which gets forwarded, right? So I only read VAST. The other is just a forwarding location. This is my cell phone. You are welcome to go ahead and text me. I go to bed with my wife at like 10:15, and so don't text me after 10 or before 7 or 8 a.m. when I get up. I am not a big texter. A text message that shows up when I'm in a meeting, and I'm in meetings most of the day or class like now, right? My cell phone will not ring. It's set to automatically go into silent mode, which means a text message comes in, it's sitting there. And if I don't look at my phone for the next day, I will not know I have a text message because it doesn't automatically come back and remind me. So I'm not great at text. Email, I read email throughout the day, and obviously when I start my email, there'll be stuff there. So email is definitely the preferred contact mechanism. If I do not answer your email in 2 days, I probably never will. So try again. It means it got marked as read, and I get about, so I also have a very aggressive spam filter. If you send me mail from some odd address, Yahoo, whatever, it may not get to me at all. My spam filter removes between 500 and 700 messages a day now, right? So, and when it goes in my spam bucket, I don't go looking for it until somebody says, "Oh, did you check your spam bucket?" Then I'll go looking for it. But if you're ever unsure, if you add the word innovation to your subject line, it will always go through my spam filter, because random parents send mail asking about the Bachelor of Innovation, which is the undergraduate degree I work on, and I don't want them to just have it disappear and think I'm ignoring them. Unfortunately, if they don't ask that, if they send me mail that says, "I have a question about your program," I will probably not get it because it's pretty aggressive. And I get 150 real messages a day, so it's not like this filtering is like keeping it to nothing. So that's why if it gets marked as read, it's gone. So these are my office hours, Monday 11 to 1, or by appointment. And I'm happy to make appointments for those of you who work for companies and whatever. You need to do stuff in the afternoon. We can also do lots of stuff by Skype, Slack. I don't do Snapchat or Facebook Messenger or whatever. But Skype and Slack are easy for me to do. I can do a few other things. So, don't feel you need to come to campus to ask me a question or have a meeting, right? I'll easily take a meeting request and do Hangouts. That's what we do lots of, right? And we can do those calls from remote or whatever. I do teach Monday and Tuesday, so this class, and then Tuesday I teach 4:30 to 7 or whatever. So I can't do too many evening meetings Monday, Tuesday, but Wednesday is, if you need to meet in the afternoon, evening, we can do that.
What if I ask you which other class you teach?
So tomorrow's class is Innovation Teams. It's an undergraduate class in innovation. And then Monday mornings I teach linear algebra. So I'm doing all kinds of different things. So the description, assignments and gradings, I already covered some of that. So not a very deep. So down here at the bottom of this, various weekly things will show up. So here it has your weekly week 1 journal, which is pretty much the assignment I just talked about. I thought I updated this. I must have, so I'm going to add a link in this when I go back home tonight, which is the GitHub's education pack. And if you click on that, then you get free free GitHub accounts and stuff. But you'll also, from that same pack, you'll get like some extra Amazon time, AWS time. You can get free MailChimp and some other things that if you want to do projects that involve a bunch of other tools, you can use a bunch of stuff. Okay, so in Canvas, so very basics of Canvas. So if I go to home, it should show, because it's so small, you can't. Normally on the right-hand side is a list of what's due coming up. So you'll be able to see, you have this assignment due. It doesn't tell you when it's assigned, only when it's due. Normally things for this class will be due one of 2 times. Either it's going to be due on like late Saturday so that I can spend my Sunday prepping for class and reviewing what you said, or it'll be like Wednesday So it's after class, you can ask questions and then have follow-ups. It depends on if I give you, like this journal assignment is due on Saturday, so that on Sunday I can read them and come to class knowing what has been discussed. Other things will be like I'll give you an extra time and it'll be due after class. Yeah.
Right now it's saying that this module is not
You don't see it, okay? I was updating it this morning. Here we go. Okay. Oh, so yeah. Here's the link for the GitHub and free software. So I was up to it's. Now it's up there. Yeah. So there should be how to use Overleaf, which I'll show you in a second. We'll show you later on today, and then the GitHub link will get you the free software. Give me an entire box to click on the link. So this will show you some of the things you can get. So you get some AWS Educate, which if you sign up for, make sure you use your UC.edu. If you have another Amazon account, that's fine. But the way the Educate stuff works, they want us to have you using your university account so they know it's not whatever. Some Cloudflower, some cards, some data logs. Obviously, you get the GitHub. You can get some web hosting. Some cheap domains. I'm not even sure what all these things are. SendGrid, so you can send 1,500 mail a month if you really want to start sending spam as part of this class. But if your research is involved with doing things that involves mail, that can actually be pretty helpful, and so on. So you get a whole bunch of stuff out of this. So Travis CLI, so you can do like testing and whatever. That can actually be useful if you've never used it. Anyhow, so back to. I can't see the buttons at the top. I don't know how to get it to go if I can't get to the buttons. I just tried F11, that did not. Yeah, Alt Tab should work. I can bring it over here and okay. Go back into PowerPoint. Is Lix? So if you want to use different platforms, yeah. So I'm going to show you Overleaf, so you don't have to install stuff. I will tell you if you're going to be doing this a lot, running MikTeX, Lex, any. So I run like Tech Live and hardcore stuff. I'm fine with you using whatever version of Tech you want. I'm not going to make you use Overleaf because I actually don't like it that much. But when my students use it, I'm going to show it to you because it's an easy way to go through stuff. So no, you don't have to use that. I like to be able to run LaTeX offline, so that I can use it when I don't have internet and things like that, which is often where I find myself typing. Okay, so I already covered that. We are now going this way. Okay, so let's talk a little bit about what is the role of research and what is research. So it should be something that, research, in my view, for you, should be something about some problem that encourages enthusiasm for you. It's not really research if you don't want to do this. Unfortunately, during your PhD, you may say, well, I have two choices. This is what work wants me to do, so it'll pay for my PhD. Therefore, that's what my research is. And that's okay. Eventually, you really want to find something you're passionate about. Okay? But if you're passionate about learning and research, that's why I have such a weird background of all these different problems, because I'm actually easily interested in things. So for me, I can do research on all kinds of stuff and still be happy about that. Some are more interesting than others. But most importantly, my long-term view for research, which we'll get through in a bit as well, it really has to be interest for others. If you write the world's best dissertation on something no one cares about, does it matter? Does it make a difference? Okay? Now, you have to be careful. No one may care about it now. They may care about it in 20 or 50 years. So it's possible that somebody will care, and you can imagine why they will, but right now they won't. On the other hand, if I wrote my entire thesis on how to make an IBM PC running on an 8086 boot faster, would anyone care? No. Right? We're not running on 8086s anymore, so no one may have ever done that, found a way to make it boot 10 times faster, but almost no one will care. So you got to find that balance as you go through this.
The area you choose to do research in, is
So it depends on how specialized you get, but more importantly, when you go to apply for positions, how narrow-minded you are. If you go in and say, I do adversarial machine learning, and that's all I do, then the recruiter might say, well, we have a general security position, but we don't really care about adversarial machine learning. Now, if that's all you really care about, then you just keep looking until you find a job that lets you do your passion. If you really have a bunch of interests and you got focused on just one, then you can break out of that. On the other hand, if you only publish in one area, then you have very little credibility to say, I can do this as well. So my recommendation is if you have multiple interests, you find a way to publish in multiple things, even if the biggest part is all in one area. So one of my PhD students who now works for Sophos did most of his PhD in what I had money for, vision and machine learning. Okay, his job is doing machine learning for cybersecurity. And we published 2 papers in that space, but most of his publications were straight up computer vision. And the other part was, when he started, he didn't know he wanted to do that. Right? So that's another thing, right? You might think, this is what I really like. My PhD started with me doing theoretical computer science because I started as a math major and theoretical computer science was math, and I was enjoying it. And I stayed in that field until I gave a talk and I realized there were 15 people in the world who cared. They were all in the room, and there's only 15 of them. And why am I spending my time to do this where, it's like it's a small clique of people? I decided I want to have more impact with my life, so I started adding new topics that I thought had broader appeal. So it won't necessarily pigeonhole you, but if you're not careful, you can get pigeonholed because you haven't shown a broader set. Hannah.
Do you have to write your thesis on what your advisor is interested in?
So you have to write your thesis in something you can convince your entire committee is viable. Okay. Now, so if your thesis advisor doesn't think it's interesting, find a different advisor or find a different topic. It generally is not good if your advisor says, nah, that's not good work, don't do it, and you say, I'm doing it anyhow. I've seen students go down this path. It is generally not pretty. Now, if your advisor says, I don't think you can do that, that doesn't mean you should change. Because if you can prove your advisor wrong and do it, then you actually have something that's like, wow, you really did something I didn't even think was possible. Okay, so it's not necessarily a bad. And you can also compromise. You can do your day job on the stuff that your bills are being paid by, and your advisor says, this is what I want you to work on, which is like for the students who are not paid by their advisor, it's called a company, and they do that, there's their day job. And then you can do a few things on the side. Personally, my PhD thesis had 3 sections, one on theoretical computer science, one on computer vision, and one on psychology. Right? I had 3 different advisors doing 3 different things. No member of my thesis committee read more than 2/3. You either read vision and psychology or theoretical, and some just read just the theoretical, ignore all the other stuff. It's all. So your committee as a whole has to sign off on everything. That doesn't mean each person signs off on everything. Although they have to sign off on the whole thing, but they might just ignore the other parts. So I got off track. So what is good research? I like to think of good research as things that are generated from the thoughts. Here's what we have now, the past isn't quite good enough, or whatever, we can do better, right? Computer science is a largely synthetic field. I can do all kinds of things. I can say, well, right, if the vision system of the human had 37 eyes, here's what I could do. But who will care, right? So if it's not practical. On the other hand, if I say, here's a problem. Our current machine learning systems aren't good at dealing with things they've never seen before. Right? They should be able to say, I don't know. But traditional machine learning doesn't. That's been part of my research for the last 10 years. Right? That problem was interesting. It's still interesting to me. It's a big part of what we do. But when we started, people were like, no, that wasn't very interesting. So you have to have a vision beyond what everyone is saying is a problem to sometimes do new and important things. That's okay. Right? Just because currently not a lot of people are excited about it doesn't mean it's not interesting. But you got to find a way to make it say, here's what's wrong with the world and here's how we make it better. And if you can measure better in some way that people care about. So if I describe the problem as making machines say, I don't know, people just didn't care. If I said, when I put a real system in the world and someone puts their lunch bag on the conveyor belt, it will not break because it's going to say something stupid, right? Then maybe they'll care about it. So you can put it together in lots of different ways. Generally, research consists of work that leads to a meaningful contribution and, importantly, and evaluates that contribution. The distinction between research and a demo is I can demo something that looks cool, but I've not actually evaluated it. So research generally involves doing some level of evaluation to better quantify and understand what it is that happens. Now, that doesn't mean you won't research papers where you won't read research papers. Even some of them are highly cited research papers that have no evaluation. But normally those are done by people who now have enough reputation that they don't care. There are no papers, so there are no promotions I care about anymore. There's no stepping stone I want to use my career for. So I can be a little bit out of the norm and say, I'm going to do something a little bit provocative. And there are people who are established enough in the field that they will intentionally do something and not evaluate it because they want to leave room for other people, and evaluation takes a lot of time, and they're more excited about new ideas than they are about actually following through and finishing up. So you can do research without evaluation once you have enough reputation that people will take you seriously. And in the beginning, probably best to make sure you do some evaluation. It needs to generate in some way a better solution to the problem. We call that advancing the state of the art. Whatever is the best at what your problem is, you need to go beyond that. Why? Because if I find a way that's 80% as good as the current state of the art, why does anyone care? Now, you have to be careful. They might be 80% better in one metric, but 120%, that is 20% better than the state of the art in another metric. You don't have to evaluate yourself with the same metrics that other people evaluated their work. As long as there's some useful metric that you can use, you might be advancing the world. It also needs to be shared and used to have an impact. If you write the world's most interesting thesis and you stick it in a drawer, no one will care. Okay, lots of the math that we look at in various points in time, right, were actually discovered by other people who didn't have the connections or the relationships to get it out, right? So things like the Fourier transform, extremely well known, was actually invented by somebody 15 years before Fourier, but no one, including me, knows what their person's name is, right? I've read about it, I've read their name, but I can't remember it. But Fourier analysis, everyone thinks about Fourier analysis. The decomposition of sines and cosines, he came up with it, but someone else came up with it and they were obscure. There was an Indian mathematician that invented a whole bunch of stuff that were then reinvented years later in other places, but he lived in a small village in India and didn't understand the impact of the or potential of the work, so no one ever knew about it. Ramachandran or something like that. A whole bunch of interesting stuff was rediscovered. Your work is only as valuable as the impact you can have on the world by getting people to get it out there. And to have that happen, you probably need it to be reviewed before most people will consider it. This has become more and more of an issue as we approach the world of the internet, where we have things like archive. How many of you have heard about archive? Okay, so you'll hear more about it even today. So archive is a place where any of you can publish a paper. Of course, it has no reviews, okay? And the majority of papers in archive have exactly 0 citations. The majority, more than half of them, have no citations at all, excluding their own authors. They'll cite your own work, but no one considers self-citations in a meaningful way. So most of that work, no one cares about. No one's ever cited it. There are lots of journals that have the majority of their papers have 0 citations. So we'll talk about those metrics and how to make them. So you not only want to make sure you publish it, but you want to publish it someplace where it's going to both be reviewed and have some level of respect. There are journals you can publish in that if I see somebody has published in that journal, I take off points when we're reviewing those candidates. Because it's sort of like saying, well, I really know how to do something in computer science, and I published it in Dr. Dobbs' journal, right? It's a journal, isn't it? It says Dr. Dobbs. How many of you know? Is it still in existence? I have no idea. No? Okay. So it was a journal in the 80s, but it wasn't a journal. It was like PC Magazine. It had weird, random things. There was no serious review. You could say all kind of outlandish things. No one cared, right? But it was called Dr. Dobbs' Journal. And people would publish in it. And I'd see it on their resume. And they're like, okay, so you published in a popular magazine. What does that tell me about your academic research? Now, if they put it in a category of their CV where it says magazine articles or whatever, I don't care. But if they try and claim it's a regular paper, right, what does it matter? Any of you could have a journal paper published in the next 3 weeks. Like, I can tell you a journal that if you pay them $2,000, they will publish your paper. And it doesn't really matter if the paper is computer-generated semi-gibberish, okay? The one thing they will now check for is that it's not just a copy of another published paper, because they've all been sued by now for having done that multiple times. And when IEEE sues them, it costs them enough money, it's not worth it anymore. But if you take random paragraphs out of a bunch of papers and stick them in, they will probably accept your paper. I mean, that's how unserious or how bad the review process is. Your paper doesn't have to read like sense. It's just paragraphs put together. There are a bunch of places where they've sent these machine-generated papers where you give this computer program like 50 keywords and it will generate a paper. And you read it as any scientific person, it's like, what? This makes no sense. It gets accepted in these places. So you will eventually have to learn how to make sure that it's going to a good place. So a couple of definitions of research. I like to point these out because you will talk with people in other fields. And in many fields, any careful or diligent search or inquiry or examination of a topic is considered research. Okay? On the frequency of the letter Q in the poems of somebody is actually research in some fields. Okay? Not what we're going to expect here, but you have to understand what are the standards of research in your field. Collecting information about a particular subject is research. So you will all be doing research, since you'll be like pulling up papers and doing, right? That's one kind of research. In computer science, well, we like to think of it as, actually I'll get to my definition in a second. So what is research? It's a combination of investigating of the past and effort in the present that will help others in the future, right? So it's really looking at what's been done, finding a way to do something now that will help people in the future. That's a broad definition. And for those of you who have not got involved with this, it is the most exciting and frustrating thing you get to do as your career. I would never not want to be a professor, right? Because research to me is one of those things I can't not do, right? I wake up at 6 o'clock on a Saturday and I have research ideas in my head. I will get up and read papers, whatever, because it's what I want to do. I'm always thinking about it. It's fun for me. But it can also be very frustrating because it doesn't always go the way you want. I've had a couple of problems I worked on at least one day a week for 4 years and didn't solve until the day I solved them, right? So you keep working through. So it can be very frustrating. It can be lots of little small steps and then all of a sudden something really big can happen. So you can't just chase big steps because often they fail. The way to get them is often a bunch of little steps to put them together. And it's a balance of building on the work of others and contributing your own work. It is not enough to say in computer science, it might be in literature, to say, here's what other people did and analyze it. You have to add something of your own to make that next step happen. And in my view, finding or developing something that impacts the world in some way. Okay, so what isn't? It isn't in computer science just playing with technology. I have seen plenty of theses which really come across as, oh look, there's this new cool thing, Docker, and I'm going to analyze the security implications of using Docker images. Okay, right? Well, if you really analyze the security implications, but if I just build a demo that shows that I can attack a Docker image, that's not really going that far. So you have to balance what is it going on. Just because you use new technology doesn't mean it's a new research question. If it's the same old research question because it's really a virtual image and I can attack a machine, then what difference am I getting, right? So you have to understand what's really interesting. It's not a book report. It is not so-and-so said this, so-and-so said that, so-and-so then this. In fact, no good survey article that's published in a good venue reads as a bunch of paragraphs, each one dedicated to a particular topic that really doesn't integrate them, right? That's a book report. Here's what these people did, not real research. Good survey papers involve some research where you find ways to connect papers in ways that weren't obvious. So you draw parallels between them in one sense and then disparate differences between them here so that the readers can draw a more interesting conclusion. So then you can actually be doing some research even if you have nothing new in the technological sense, new in an algorithm sense, you have a new point of view. That is actually the standard in many of the humanities, where it's really analyzing other people's writings and coming up with a new point of view from them. And you can get away with that for a survey paper. Generally, that's actually something you put in a bigger paper, and it's a smaller section, but it's possible. It definitely isn't just a programming project. It isn't, here, I built this, isn't it cool? Which is a little bit like playing with technology, but in this case, you programmed it. It's not commercial product development, although both programming projects and commercial product development can be done as part of research. The research is what's underlying them and how you study it. So if I built that cool program or this commercial product and I study it and I show it's better than anything else that's out in the research literature, not necessarily what's on the market. There's lots of things in the literature that aren't on the market. And unfortunately, there are lots of really good things in the market that aren't in the literature. So you can't always just say, well, this is better than this paper, because the answer to how do I build fast databases might be better answered by Oracle than some internal research publication of a university that has 2 servers running on a large, they call a large database with 1 million records, right? You have to figure out where is the real state of the art and make sure you're addressing that problem. And obviously, it's not doing what others have done. It is unfortunate, but if you miss the publication deadline of a conference and somebody else publishes at that conference the same idea you had, you've pretty much lost your ability to publish that. Okay? If there's 2 publication venues and their publication comes out a week before your paper gets submitted, your paper will likely be rejected as not novel compared to that paper. Reviewers are pretty good at knowing what is the state of the art, and unfortunately, your paper will sometimes be rejected because there's a paper that was submitted that came out after your paper was submitted, and the reviewers forget about the timing. And then they'll say, no, it's not new given that other paper. Because in their view, they read that paper before they read yours. Therefore, yours wasn't novel. You can still argue about that one. We'll come back to that when we eventually talk about research and whatever. So lots of times people will talk about what's trying to do fundamental research. And I like to address this because you might hear an advisor talking about fundamental research, and you can't go back and tell your advisor, I'm sorry, Dr. Bolt said or Terry said, this is the definition. I'm giving you my definition, but I'll start with really what is the sort of definitive answer that many people fall into, especially outside of computer science, but it's the study of something in a pure form with no application that leads to a result that has some scientific value as soon as it's been accepted by the scientific publication, sort of a scientific community. So in physics, lots of people talk about fundamental research in physics, which isn't trying to solve some problem, it's trying to understand the world. And in physics, that actually makes a lot of sense. We're trying to understand, what is this, subatomic particle mean? We don't care what we're going to do with it yet, right? In the 20s, when people were starting to understand quantum mechanics, they had no applications yet of quantum mechanics. It's just, these electrons are not behaving like we think they should. Let's develop a theory and stuff for them. And if it's truly fundamental in that sense, that can be okay. But there were also lots of things studied in the 20s in physics that you've never heard of because they had no value and no implication. So it's also a big game to decide you're talking about it fundamental. And unfortunately, there are many people who come across and actually who really believe that fundamental research is more important and somehow better. That is, they're doing something important, and because you work on an application, they think that's lesser of you because you're not chasing the fundamental problems. And I've dealt with those people all of my life, and I can tell you that in the long run, if you keep doing good published work, even if it tends to be towards applications, they'll eventually learn to respect you, even if they don't understand it. On the other hand, more of them fade because they never do something significant enough. So the second answer is it's something that has some scientific value if it interests people, and if it's novel and has some genericity. That is, it can be generalized beyond one problem. And that's not necessarily a bad answer. My answer is that, or the third answer that people say, and I say the definitive answer is a result that helps solve problems or solve a problem and has some general scientific value cited by others, right? So if you do something, and actually let's just say problems, not one, because I'll come back to that, and it has some general value. So if I come up with the very best fingerprint sensor that's good for people who work with bricks, it's a pretty narrow problem, no one will care. If I come up with an advancement in fingerprint sensors that is better than most fingerprint sensors in almost any way, maybe people will care, right? Even though it turns out that the problem for many fingerprint sensors are they don't do well with people who do manual labor, right? That's really the hard problem. But if I only test it on that subset of the population, no one's going to care. So I got to find a way to make it general enough to make them interested. Most problems, and so the most interesting problems, the most difficult and often the most interesting problems have often been raised by applications. For example, medical applications, large-scale applications. They push the limits of what we can and cannot do, and then you sometimes have to go back and figure out how do we actually solve those problems. Now, one of the reasons they're difficult is because the real world is complicated. If I want to do medical applications, there's a lot of different people. And so it might work in this category of people and not in that category of people. Something that's truly general will work across large populations as opposed to this narrow subset, just like I talked about in the fingerprint example. You want to talk about making it general, then sometimes it becomes very, very difficult. And in solving many of these problems, people have then often developed very interesting theoretical scientific developments. So a bunch of the sensors we have in the medical imaging field, things like MRI and CT scans, came about, and when people said, here's our problem, I need to see inside the body. How can I see inside the body without cutting it open? You start asking questions about how I can image, and so you develop all these interesting technologies that led to significant scientific questions about how to reconstruct an image from different viewpoints, or how to use the decay of the magnetic field of a hydrogen atom, which is a really small amount of decay, but the magnetic field possesses, and that's how MRIs work, right? No one was asking the question, we already knew that electrons spin, but what we could do with it was a different question, and so medical applications drove some very interesting questions that go into that. So don't worry that you're working on applications. In fact, my final bias is a fundamental research is something that will help solve multiple real problems. And if you only solve one problem with your research, or no problems, then it's not research. It's what I would call speculative research. You think this will have some value someday, but you don't know that. If you solve one real problem, you have some value. If you solve multiple real problems with this idea, it must be broadly applicable. In general, therefore, it has real research value, and that's the most fundamental problems. Man, I got to go faster. So I'll skip over the comics, they'll be in the slides, but lots of people talk about differences in research. If you don't know about the PhD comics and you're looking for a little release, just go Google PhD comics. You'll find lots of things that are oddly applicable throughout your career.
Is it okay to do a research paper on why something can't be done?
So it depends on, so if you can prove it cannot be done, then yes, it's interesting. My first paper was a proof of something my advisor told me to work on, and after a couple months I told him it can't be done. He said, I think it can be done. So I went out and proved it, and then it was publishable as a paper. Right? To just say, I don't think it can be done, no one cares. Right? Unless you're the world's expert at something, and then maybe lots of people say, yeah, I'll go someplace else because this guy knows more than I do, or he or she knows more than I do, and I don't want to go down that path. But if you can prove it cannot be done. So there's lots of, in the theoretical computer science place, lots of things, right? Things like the halting problem. If you've not heard about the halting problem, right? It's a really important problem in computer science. It proves that there are problems no computer can solve, okay? Gödel's incompleteness theorem proves there are things we can state that cannot be proven within the formal mechanisms in which we can state them, right? So there exist things we cannot prove. We proved that. So there's all kinds of, but if you can prove that this can't be done. Now, in a pure computer science point of view, you might actually be able to prove that this information is insufficient to make this good an approximation. No matter how you use this information, you can't solve this problem the way you want. That's interesting if you can prove it. If you just haven't figured out how to do it yet, right? Like, so, I told you I had a problem working for 5 years, right? 4 years and something, right? Each time I tried a technique and it wasn't good enough, okay? That doesn't mean there didn't exist a good enough technique. I just kept going through. I tried like 15 different things until I found one that worked, right? As Edison, right, is often misquoted as saying, he found 10,000 ways to not make a light bulb, and then he found one that worked, right? So he didn't prove you couldn't make one. He just, these 10,000 ways didn't work. So you got to find a balance in there. But in the security space, there's lots of things where you can prove this cannot be done, right? Because of one category or another in terms of your assumptions. That's also the caveat. Lots of things where you prove something is optimal, which is another common thing. This is the best way of solving it. Or when you prove it can't be done, you start off by making a bunch of assumptions. So if I assume that P is not equal to NP, then there's a class of problems I can't solve in a reasonable amount of time because I can prove they're NP complete, and then you can't solve them fast enough. On the other hand, if you believe in quantum computers, that if you believe that quantum computers can solve all NP problems, which is also not necessarily true, but if you assume that, then you can prove that I can break RSA cryptography with a quantum computer. But you've assumed something that may or may not be true, right? So you have to be careful what you assume to make your proofs work. Let me get off again. Okay, so who does research? I'm going to skip over this. The one thing I will talk about is most research today is done in teams. We'll actually have at least one team writing assignment in this class because it's fun. No, because it's fun to watch. Well, that can be fun. Team writing is a very different skill than just working on your own, but most large-scale research is team-oriented these days, and so you have to learn to work with other people in both doing research and about writing that research. And it's much more interesting when you're trying to write a paper and somebody keeps editing that paragraph, and you have to work through that. But the multiple skill sets and division of labor is actually very important. And then there's the different skills that people will bring in terms of their own strengths and weaknesses. So in reality, you might actually have a team, like the guys who invented the Schottky diode, whatever, which Schottky was one of 3 people who were involved in the project and actually got his name on it, most of the credit. But he was the manager at Bell Labs. There were people underneath him, one of whom was a theoretician, one of whom was more like a tinkerer in the lab who could build anything, but didn't actually understand. And all 3 of them were necessary to actually make it into what it eventually became. Schottky would not have designed his design, which was actually more efficient and cheaper to manufacture, if the other guys hadn't come up with the first design, which actually worked, and for which there was no known theory. Right? The theory guy kept saying, but there's no reason to believe this will work. And the other guy's like, well, let's just try it and see. We'll see how it goes. Right? So you can bring lots of different skills into research, and that's been going on for a long time. We have both PhD students and MS students and undergraduate students. Well, there's no undergrads in this lab. I do research with all these. I have actually done research with high school kids, right? Research to me is not about what is your level of education, but how long have you been working in this problem and what novel insights and whatever you can bring to it and how hard you work at it. My experience shows me that when somebody starts on a problem, it's around 2 years before they finally have good research insights. That's not 2 years of full-time work, it's 2 years of constant exposure to the problem, and then eventually things really start clicking. It just takes a while. I like to think of it as trying to juggle balls. When you first start, you're very uncoordinated and not much happens. And you can't really get research to happen until you can keep all the balls in the air at once, and then all of a sudden it clicks. And if you've ever tried to learn to juggle or lots of other skills, the learning curve is very often like nothing happens, nothing happens, nothing happens. Hey, this is easy. Right? And then you can't remember what it was like to not be able to ride a bicycle or to not be able to juggle, right? You just get it one day and something just happens. It takes a little bit of while, which is why this class is supposed to be taken early in your PhD. Some of you are in your 3rd year or whatever, right? If you've not been working on research and publishing or whatever, you're a little bit behind the process because you're just getting a later start. Doesn't mean you can't finish, but in my experience, it's 2 years from when you start that before you start really publishing and making stuff happen. You can get 1 or 2, as a member of a team, you could all publish this semester because you can join somebody who's farther along in the process and make it happen. Actually, I guess I should talk about these. So there's different types of research. We'll talk about quantitative research. This is where you use mathematical models, software, statistical analysis, formulaic and numerical models to analyze the results. Okay, these results are quantitative by the name of it, right? And these tend to have very quantitative orientations. So our goal is to say our solution is n% better than somebody else's. Okay, you're solving problems other people do. You're using models and numerical techniques to somehow improve on what that solution is. The main approach can also be discovery. You have to just be careful if I'm discovering in a synthetic world. I can make a world where gravity, right, is inverted, right, where things repel each other. I just can't actually ever test that in the real world because we don't have that, right? I can't necessarily make large amounts of the world where laws of physics don't apply. I can't make them where laws of computing don't apply, right? I can't have an algorithm that can output the answer faster than it can read the input, right? You can in a quantum computer, right? And now people are trying to make those things where it guesses the answer before it's seen the problem, okay? And since it can generate all possible solutions, that's somehow potentially possible, just not very pragmatic, right? I can see how that goes. So you have to be careful what you assume when you do these kinds of models if you're doing it all in the modeling world. And if you make one mistake in your model, you get results that are completely useless. So be very careful if you get on that path, because you have to have ways of checking things along the way or you get results that can be very dangerous. Qualitative work tends to use non-numeric techniques to analyze results. So qualitative research is very common in some areas like security policy, right? Not security technology, but security policy, or in software engineering, where there's just no good way to build a simulation of 1,000 programmers programming and see how well it really works. Because in fact, what matters most is the personal element, the people element. So you have to work on those things and often come up with qualitative ways. Now, the fact that it's qualitative doesn't mean that there can't be some quantitative analysis. I can measure performance of a few things, but most of the analysis will be qualitative. And in fact, when you mix the two, you get something called, in some fields, pragmatic methods, or in other fields called mixed methods, where you have some balance of qualitative and quantitative. And I would actually say this is the biggest area, the biggest way that everything I said was qualitative. In computer science, almost all of it is mixed because you do qualitative with some quantitative piece because people want to see numbers. We like numbers. We find some way of drawing graphs and making them good. A kind of research that is not done very much in computer science, with the exception of various research organizations which have a particular agenda. So we call it advocacy or participatory research methods, where you generally have a predefined agenda. Okay, and I would actually say there are definitely some people in various places, like in the blockchain community, where people are really trying to push, here is what blockchain is going to do. Has they shown it's going to do it? No, but they're focusing their problems on showing it's going to do it. Same is true in quantum computing, right? People are out, the agenda is to show that quantum computing can do these things. Some theory says they can, some call questions, it doesn't matter. They start off with a very focused method, and their research is to answer this question. It's called advocacy because you're advocating a particular outcome. Lots of people in science dislike this kind of work because you should be objective as a scientist, and the results should go where your data takes you, not that you should torture your data until it tells you what you want it to do. And when we get to statistics, we'll talk about that. With the right experimental design and reasonably vague data, you can draw all kinds of incorrect conclusions and present them in a way that will convince people that they are true. Right? You can use statistics, right? There's lies, damn lies, and statistics. Right? That's the and I'll talk about that because you need to be aware to recognize when other people do it. I am not teaching you how to do it so that you can use it inappropriately. Just like lockpicking is a skill you should understand so you understand their flaws, not so you can break into people's houses. Right? Similar methods, and we'll get to those. So when we talk about approaches to CS research, by far the most common thing is attack a known problem, find comparatives to solve it, and then somehow show your solution is better than the previous, right? So the problem is well known, the comparison tools are well known, and you make an incremental improvement. The next most common is to formalize a new problem and then attack it and find and compare tools to solve it. This is by far the easier way to get something published that no one will care about, right? Because if I invent a novel problem and a novel metric and no one cares about the problem, then I might get it published because it's novel, and then after a little while no one will care because they recognize it's novel because no one cares. It's not that no one could solve that problem before, it's that no one cared to solve that problem before. So if you go down this path, just make sure you choose something that people will actually care about. On the other hand, this one almost always satisfies it's novel, and if no one has solved it, you have the best solution because no one has ever solved it before. So you'll easily be at the state of the art for this problem. The top one has the difficulty that while lots of people know it and maybe lots of people care, really smart people have already worked on it. And you can come up with your 15th algorithm that isn't better than what's already out there, right? And so you can spend lots of time to get a result that won't go anywhere. So my recommendation is you find, as you explore your path, something that has both of these somewhere in it, right? Attack a big problem, but also invent a new small one and make sure you can solve it. Because you eventually have to publish in our PhD program. It's not a question of if you publish, it's a question of when, before graduation, because you have to, right? And it'll have to be in a good enough venue that you can't just buy your way out and say, oh look, I have a journal, they published it, it was only $2,000. Okay, and then there's another one where people will play a game where they build a new tool and test it in your own private data. And you will see this in various places. The fact that you see it in places, generally itself an indication it's not a very good place. But sometimes you'll see it in really good places because the people who built this new tool and tested it in their own private data have reasons they cannot share that data. It's especially true in the medical domain, but it's true in other things where software engineering, there can be like corporate secrets. They will not let you analyze the security of the actual Northrop Grumman network and publish about it. You may be able to analyze it, but you can't actually talk about the vulnerabilities in publishing on it. So they have some test data that will be out there. This is really a dangerous place to go. Turns out that lots of the times when I see this in good venues, it's places that have such an established reputation, people are willing to believe them when they say it was tested on this private data. When Facebook does face recognition on 4 billion faces, well, none of us have 4 billion faces. They're not going to give us the data. There's no way for us to replicate it. But they really do have 4 billion faces. We have reason to believe that they could run that test that no one else can run. And it's interesting to see the results when you get to a problem that big. So people will publish it. But in general, it's tough. So I really recommend you stay away from that when you get started. The rest of today's agenda, which we'll come back to after break, we're going to look at some common tools for the course, LaTeX, Zotero, and Get. So how many people have never done anything in LaTeX? How many people have never even heard of Zotero? Everyone, okay? How many people have no idea how to use Git? Okay, that was my expectations in all three of those. So LaTeX, Zotero, and Git will be the order we'll do them in. Take a break, be back by about 5 after. 10 minutes. Well, so you can take 10 minutes. I will start with LaTeX, and you already know a bunch, so it's okay.
Slides be online.
I will put them inside of Canvas. I don't want them publicly up there because I'll put them on Canvas. And obviously there will be videos of class as well. So, but sometimes it's faster to go through them. Yeah. Come on, where'd you go?